Hello everybody, hope you're having a great day, and now we are continuing our discussion on the damped harmonic oscillator. We're going to see how these functions behave when we vary the parameters. So this is a supplementary video to a video I did on the damped harmonic oscillator, and we wrote out the differential equation for the damped harmonic oscillator, and we solved it for the three different cases, and those cases were overdamping, critical damping, and underdamping. So this first case is the overdamped case, and for that case we arrived at the solution that x as a function of time, x is the distance from equilibrium and t is time, and gamma is our damping coefficient, and alpha is, well, it was a square root of some stuff, but it's effectively how different is the damping coefficient relative to the force constant. But it's still the case where the damping coefficient is, well, the square of the damping coefficient is greater than the omega squared. Anyways, we're going to see how these functions react. So we had these constants C1 and C2. We're just going to set those equal to 1 to keep things nice and pretty. The damping coefficient, if there is no damping, our function will never go back to its equilibrium position. It's basically like you move an object that doesn't act like a harmonic oscillator, and it just stays there. But if it does act like a harmonic oscillator and there's damping, here's what happens. As you make the damping larger and larger, you approach the equilibrium position faster and faster. And remember, in the previous video I gave the analogy, it's like punching a solid object. Well, solid objects have very high damping coefficients. I mean, they're going to act like oscillators, sort of, but not really, because the damping coefficient is so high, they almost immediately return back to equilibrium. And this damping coefficient is actually, our whole function, this blue function, is a sum of two exponentials, these two exponentials here. Let's see, when we increase the alpha parameter, we see, oh, now we can see both exponentials. So we're effectively making one of these terms larger relative to the other, but the blue is staying the sum of both of them. And what happens when alpha equals the damping coefficient? Well, turns out we never return back to equilibrium. But mainly what I want to show is, as you increase the damping coefficient, you return to equilibrium faster. So that's the overdamped case. Now let's do the critical damped case. And the critical damped case was when all that stuff in the square roots equal to 0. This is the solution that we got. And again, gamma is the damping coefficient. Alpha and beta are just constants. We'll set those equal to 1. So as we vary gamma, let's see what happens. Can't really tell what's going on yet. Okay, now we see what's going on. Okay, so in the critical damped case, the larger your damping coefficient, well, again, the faster you return to equilibrium. But see, initially, this is different than the overdamped case. In the overdamped case, immediately you start decaying back to equilibrium. Critical damping, initially you go further away from equilibrium, and then you slowly return back to equilibrium. So that's the critical damped case. And in the extreme, the critical damped case almost seems to match the overdamped case. It sort of looks like a Gaussian curve too, which is interesting. Okay, so that's the critical damped case. Now let's do the most interesting case, the underdamping case. Okay, so this was the equation we got for that. And we did some trig identities and things like that. But this we'll see what happens. Okay, so omega is the natural resonant frequency of our material. Um, let's make that 1, just so we have something there. Okay, and now there's no damping. Well, if there's no damping and we increase our frequency, we see that we just oscillate back and forth forever. This is just like the simple harmonic oscillator. Phi is a phase factor, we don't need to mess with that. And gamma is still the damping coefficient. So what happens if we add damping? Well, we see our oscillation eventually decays back to 0. And it's enclosed within this exponential envelope, which is this exponential part out front here. So that describes the orange thing. The blue is, well, it's described by the whole equation. Just the cosine part. Well, if you want just the cosine part, you can set gamma equal to 0. And that was the case that we had for this simple harmonic oscillator. So that is a little insight into how those functions behave when we vary those parameters. If you want to mess with this file and you have Mathematica, I will be happy to send this to you. Just shoot me a message. Besides that, thanks for watching and have a great day.